Hey everyone, so in this video we're going to look at solving rational inequalities. So very much like the polynomials in the last section, we're going to find our x-intercepts. This time we also have to find undefined values. So for the polynomials we just had to find where it was crossing x, but this time where it's undefined can also result in a sign change. And then we'll do the bit where we draw the number line, we'll pick our points and test those and see what satisfies the inequality. Here, the one thing we do have to be careful to not include any of those values from the denominator. So that's pretty much the one difference between these and what we've already seen. Okay, for this first example, we got for the numerator, that would be our x-intercept. And so that would be at x equals -1. And then for our denominator, this is where it would be undefined, and that would be at x equals 3. We have an equals on there, so we're going to want to include zeros. So at -1, that one's going to be solid because that will be included because that's where it equals 0. But at 3, I want to be careful to keep that as an open point because if it were 3, I'd have division by 0. So that's where our horizontal asymptote is. We cannot include that. So then if I do test points, I'll test 2, 0, and 4. So if I put in -2 here, I would have a negative over a negative, so that will be a positive. If I put in 0, I have a positive over a negative, so that will be a negative. If I put in 4 plus 1 is 5, 4 minus 3 is 4, that's a positive over a positive, and I have a positive. Coming back here, I want the greater than or equal to zeros, so that means I'm going to want these positive regions, and I want to be careful not to include that 3 because of the division. So in interval notation, we'd have -infinity up to -1, the bracket, union, and then 3, on out to infinity. This one's pretty similar. This one's a less than. The lessons are actually a little bit, or the ones without an equals to is actually a little bit easier because then all the endpoints are open and you don't have to pay much attention. So here my zeros are going to be on 2 and -2, and those are both open dots. So that's my zeros. And then if I toss in -3, I get negative over negative. So you see I'm doing that, I'm just going -3, that'd be negative, negative makes positive. If I put in 0, negative over positive, negative. And if I put in 3, positive over positive, positive. So this time I want less than 0, so now I want the negative regions, and that's going to be inside there. And so for these ones, we're just going to have -2 to 2. Okay, and then for this last one, we got to do a little bit of factoring. So x plus 3, the denominator is going to be x plus 2 and x minus 2. So I'm going to have zeros on -3, and that one will be solid. I'm going to have open dots on 2 and, or sorry, -2 and 2. And so I'm going to test, this time we'll have to do a fractional one because we're two integers right next to each other there. So I'll test the -4, I'll test 2.5, -2.5. 0 is always nice, and 3. And I like to look at it down here just because it's easy to see the signs. So here, if I put in that -4, numerator's negative, negative, and negative. So 3 negatives would make this part negative. If I put in -2.5, -2.5 would make that positive, and then negative and negative. So 2 negatives will make this region positive. If I throw in 0, I have 2 positives and a negative, so that is negative. And if I throw in 3, everything's positive, so that will be a positive. And this one we want the greater than or equal to 0, so we want a positive region, so we want here and just in between there. So in interval notation, that's going to go from -3 to -2, and then parentheses on the 2's, and on out to infinity.